And I suppose part of the QbD component of that is that they ultimately used what is a very nice way to present data, this idea of a response surface, showing in this case the free base yield, so the tendency for this disproportionation to occur as a function of the dissociation constants of the acid and base. So this is the way that statistical DOE data are often presented, but there's no DOE going on this screen. It's all theoretical calculations using a dynamic DynoChem model with the input parameters based on, like I say, those Ka and pKa values, and also information about the particular excipients and their moisture content. So really from that response surface, it's possible to read off the conditions which will cause or prevent disproportionation at any time. So it's really a very good piece of work, but I think it also shows, how far downstream you can go with this approach, potentially even into the stomach, to have a look at how these reactions begin to occur once the tablet is in the human body. The other interesting observation that we heard again at AICHE this year was from Jose Tabora and some of his colleagues at Bristol Myers Squibb, who talked about appropriate ways of displaying data and sort of bracketing your process so that you're very confident that the results will fall within a certain range of upper and lower limits. And one of the motivations behind this talk from Jose, which was paper 182b, was that regulators, and in fact a lot of ordinary human beings, are able to understand these kind of data presented in a response surface with just two dimensions, two horizontal axes and one vertical one, pretty readily. And it gets complex for us when there's a lot more dimensions on the plot. So the idea from Jose and his colleagues is to effectively draw two surfaces on the plot, so still to just plot against two factors, but potentially have lots of other factors varying. But then the two surfaces represent the best and worst combinations of the factors that you're not plotting. So what we're looking at right there is actually a reaction time, the time before we reach the in-process control limit for a hydrogenation, plotted against mass transfer coefficient and catalyst loading on the horizontal axes. So basically the time is shortest down here at the bottom right when we have good mass transfer and lots of catalyst, just the way that you would expect it to be. But because there are two surfaces, it means that we're bracketing a whole range of other variations, not in KLA and not in catalyst loading, but in things like pressure and other variables like that. But if we pick the worst case calculations for those other factors and the best case calculations for those other factors and make them on a surface plot like this, we effectively bracket the best and worst outcome that we can reasonably expect from the process. So we might well have a very nice process developed at lab scale that gives 95% yield and almost no impurity, but the issue is, how do we translate that to commercial equipment? And we would reasonably expect the chemical kinetics and other scale independent factors like the solubility of the hydrogen to be constant, independent of scale. But mass transfer rates, so the quality of contact between the headspace and the liquid, heat transfer rates, how easily we can remove or add heat to the system, these would be highly scale dependent. And an interesting variable to look at in the context of those two scale dependent factors is the amount of catalyst, which is almost like a dial on how fast the reaction is. So low catalyst, slow reaction, high catalyst, fast reaction. So a dialog appears shortly after I do that, saying DynoChem is now running the scenarios. So the Excel file has been read by our executable, the equations have been generated, the 121 virtual experiments have been set up, and now they're being run one after the other from time 0 all the way to actually 1800 minutes of runtime. And all the various profiles for imine and amine and so on are being calculated by the model as a function of time. And then finally, when the calculations are finished, I get a big table of results back in Excel telling me all of the factor levels that were used for the simulations. So 11 levels of catalyst loading, and then also 11 levels of KLA. So that's the left-hand frame of the picture is showing me the inputs that I varied, and then on the right-hand side I get the final values of my responses. So how much starting material, how much imine, how much product, how much impurity, and so on are present. So I'm going to just grab everything from impurity to the left. So this is just, you know, if I wanted to make a beautiful graph, I would copy and paste these results to another application that's good for making nice graphs. But because I'm in the middle of a project here and I want to get some insight into what matters for my problem, I'm going to do a quick plot in Excel. So you can just select all of the columns, the ones that include the results and all of the things that we varied, and then you can again go to this DynoChem menu and say you want to plot the results on a pivot, so-called pivot chart. Initially that doesn't look too interesting, but that's because the wrong things are on the horizontal axes. So if I just check a few boxes here, I can say that I want catalyst to be on one horizontal axis and KLA to be on the other, and then I have to just click and drag a few labels down here so that, you know, I'm basically getting a 3D plot definition on this pivot chart, and then finally I get my first graph. So what this one shows is the percentage impurity, really effectively the relative area percent of impurity to product, plotted versus KLA, varying from typical pharma hydrogenator to bus loop reactor, and also versus catalyst loading, varying from a kind of a base case level of catalyst loading to a fairly high level of catalyst loading. And you can get a flavor pretty quickly for the fact that at low KLA values, almost irrespective of the catalyst loading, I'm making a lot of impurity, whereas at high KLA values, again, pretty much irrespective of the catalyst loading, I'm not making much impurity at all. So this is how you could, you know, see what level of KLA, or possibly even what combination of KLA and catalyst loading forms a design space in terms of avoiding the impurity for your particular process. I'll just show a little bit more about how these graphs work. You can uncheck the impurity so that it's not plotting impurity anymore, and then you can just check another box, and this one here is looking at the time it takes for the nitrile to get completely consumed. So it's like how long it takes for the process to pass the IPC limit, if the IPC is something like 0.1% impurity. And again, there's a logical behavior here. We can see that at slower mass transfer rates, low KLAs, it takes a long time, 1200 minutes, for the starting material to get consumed, whereas at high KLAs it all happens a lot faster, a matter of an hour or two, particularly at high catalyst loadings.